me and my colleague were going to come here to present about Akka and Mainframes, and some type of, we can talk about some practical patterns or integrations that we have done. My colleague, however, could not make it out, so I'll be here to attempt to present the presentation, answer any of your questions, give some insight, and hopefully not fail while doing that. So, just FYI, before I go further in the presentation, I don't want people to overreact about what is actually coming up in the presentation. This presentation is not about deploying the Akka system on the mainframe, right? Wherever you can run the JVM, you can probably run an Akka system too. It's all JVM-based technologies. So if anyone thought this was going to be about Z/Akka, raise your hand if anyone gets that reference. Cool. So what I'm going to be talking about is how the Akka topology, and in particular the Akka toolkit, which is one of the main implementations of the Akka topology and the Akka concepts, along with other reactive concepts from the manifesto and from just general principles, can be used to integrate or flush out or expose business functionalities that have long been on the mainframe. So I'm going to go ahead with some patterns and use cases. So by a show of hands, how many of you guys are familiar with the idea of a TCP socket servers on the mainframe? Yep. So a lot of green screen applications are usually run off of a socket-based connection. So one of the projects that I worked on previously, and what me and my team had worked on, was this idea that there was a bunch of functionality in green screen commands and green screen in socket-based commands that had previously been integrated through various spaghetti ways over many decades to create various business flows, whether it be a multi-tiered screen-based flow, or whether it be something that was ported over to a thick client in like the early 2000s. So we were asked to come up with a way, hey, if given a series of socket connections, and given these dependencies around them, given these limitations around them, how could you expose them and utilize them to create a more tolerant system, a fault-tolerant system, create a more usable system where more users could be onboarded. So by what we came up with was a stateless solution for socket connections. So some of the dependencies that we had were, for example, the socket server on the mainframe, on this particular mainframe, supported a persistent socket execution model. So what that meant was that so as long as the connection was initially established, right, just some initial establishment of the connection with like a acknowledgement from the mainframe socket server that yes, everything looks fine, you can then use that socket connection to execute any variable command for any particular user. So what that meant was that if we were using an actor to represent that particular connection, it didn't need to keep alive the connection, right? It just needed to open and just reuse. Of course, if there was any type of authorization required initially to log in a user, for example, any connection could be used to do that authorization. And I've also defined some Akka-based method hooks. I just talk about how when the actor starts, you establish the connection to the socket server. When the actor receives a message, you execute the command that was inside the message. And whenever there's an error, you leverage a supervisor strategy. But you have to be cognizant of what the supervisor strategy does. In this particular case, in a stateless approach, like I said earlier, all you had to do was just make sure the TCP socket connection is just kept open and acknowledged. So if you believe the error that is coming back from the socket is something that requires a restart. But if the error is worse, if it is something like a complete hang-up, then you should disconnect and probably throw a more fatal exception upstream. and allow the user experience to drive what you should do in that situation, whether it be to restart the page or restart the entire flow all over again. Yeah. I think it's also important to mention that if with a misaligned supervisor strategy, like maybe throwing exceptions that then get caught by supervisor strategy that do more frequent restarts, be cognizant that in a socket server implementation, the re-establishing connections at a much higher rate can actually overwhelm a socket server as well. So this is just a pretty simple diagram of a simple stateless approach to making socket connections. Once you've established a connection, you can just send over commands. They can also be grouped, the different functionality, like the different mainframe commands, whether it be a view command or a CRUD type of operation command via a mainframe, or whether it be a more complex command that someone developed on the mainframe many years ago. They can be grouped in separate actors that can be defined by that functionality. Nothing groundbreaking there, where you can have a stateless actor that just does a particular functionality well, and then drives that behavior to an actual another actor system that may actually be keeping track of all of these stateless socket connections. There's another approach which is stateful. So this happens when the mainframe that you're working on and the socket server implementation on that mainframe actually requires that socket to be tied to a particular user. So imagine John Doe comes online, and he needs to, AKA, create his space within the mainframe, a user session on the mainframe, so he can begin doing some work. That means that from an actor perspective, if the actor is acting as the holder of that connection, that means the actor does need to keep alive that particular connection for that user. That also means that the actor, you cannot just have a pool of actors available to handle all that load, because you may have more users who are coming online. That means you need to create actors on the fly as well. So when an actor is created, you establish the connection to the socket server, and you also establish the user session. That means that this becomes kind of like a stateful actor as well, that you actually hold the authentication information for that user and create an authenticated session. When the actor receives any particular message, it will execute the command for that user. And if an error occurs, errors such as, for example, an error that requires the connection to be restarted for some reason, you would, because it's a stateful actor, you would just reestablish the connection with the straight authentication details. But if it's something more fatal, you can do a poison pill. And this leads into the next topic, sharding. So sharding is possible in the Akka toolkit via the Akka clustering approach. So one of the standard use cases, the out-of-the-box use case, is a cluster singleton, AKA one JVM, one cluster, and you just create actor within your JVM. That is a singleton cluster. So this particular approach is something that we actually did initially get all the way up to production in this particular use case. We leveraged a capability such that as the users were logging in and entering the credentials on a particular part of this application, we took those credentials and we said, okay, we're going to create user ABC or user John Doe actor. Create it, establish the connection to the socket server. The socket server, of course, had all the commands to execute with the mainframe. Once the login is successful, you then create a reference marker, tie that back to that particular user, and as subsequent requests come, you route that particular request to the appropriate actor. That reference token can, for example, in the actor topology in the Akka toolkit, you have actor refs. You leverage the actor ref in the cluster singleton approach to route the command to that particular user's actor, and you execute the command again, or whatever command that they had requested. This is more impactful in a cluster sharding approach, where then you leverage multiple nodes, multiple JVMs to deploy a bunch of users, actors across your deployment ecosystem, whether it be Kubernetes or whatever approach that some people take. This is pretty much the same slide, but I think what just makes it more unique is that where that actor system lives, it becomes a distributed actor system, right? You have an overall actor system in your application space that can live on multiple JVMs. When you find John Doe's actor, he could be on machine number 23. The actor ref is a very powerful tool to send that socket command to that actor without having to know the physical location. And then leads into another approach, screen scraping. So far, I've just been talking about just executing TCP-based commands. But screen scraping is also a fundamental approach of getting business value outside of existing mainframe capabilities. I think, like I was saying earlier about this presentation, it's not about, or as previous presenters have done, talking about destroying or moving parts of your mainframe business logic out of the mainframe. There are going to be times when that's not possible. In the intermediate state, you still need to keep a lot of flows, a lot of business flows and data flows inside the mainframe. That includes UI and UX flows, or UI flows in particular. The green screen as used by internal users at a particular company or organization, or as used by other partners. So this, for example, it's pretty similar to the last approach, but the idea is that you again deploy something on the mainframe that enables a screen scraping approach. So 3270 is one of the main green screen flows. 3270 emulation. 3270 being the actual protocol, the IBM protocol that is used to send over commands and data. You would do the same thing. You would actually create an actor and leverage the Akka TCP toolkit and have all the benefits of back pressure and other reactive tooling. But I think what it comes down to it is that it just exposes screen scraping. And screen scraping has been derided previously in like some of the more modern conventions and conferences that, oh, just do a complete refactor or a replace. But what I'm trying to say on this stage is that it does hold major business value in the intermediate state. It allows you to put one step forward and go into the microservices or reactive world. Similar slide. You got RPC'd. Yay. So RPC, remote procedure calls. Another possible integration flow with your mainframe. And the way that can happen is through commercial software. So there are commercial software out there as provided by IBM and others that actually can sit on top of your mainframe and can expose functionality through remote procedure calls. An example is the IBM's ONC RPC product. Okay, you have a product that exposes the functionality through RPC. Now with the understanding that we have about the reactive concepts, you can actually connect to that RPC server using a reactive RPC client. With all the benefits that come with that, you can actually now enable more different functional flows to be orchestrated with that mainframe. You can have different number of users come online. You can control the number of users that come online, and this actually gives you pretty much more business flexibility. Now, I want to be cognizant that this may not always work in the sense that not all mainframes have this capability to actually deploy some RPC servers. Have to be cognizant of that, and of course, your toolkit selection also matters. For example, the main RPC toolkit on Akka is Akka gRPC. But gRPC is not a standard RPC client. It is particular to the gRPC protocol. Yep. Now I'm going to move away a little bit from TCP. I'm going to go and talk about the strangler approach, which has been talked about in some depth in previous sessions. But the idea of taking your existing services, whether it be commands or services, and over time moving them upstream to different layers in your application stack. So your mainframe exposes commands, exposes operations and data through various network interfaces, whether that be TCP, SSH, invocations through an ESB of an IMS transactions or COBOL programs. You can put an actor system on top of the mainframe, have it orchestrate and execute all of your new logic, pretty much similar to what an ESB would have done 10, 20 years ago, but with the idea of the actor topology. Now that you can have actors interconnect, intertalk, and do reactive back pressure and fault tolerance, it just creates different value. When the actors talk to each other, that sounds very similar to event sourcing, and I'm going to be talking about that in a few minutes. Below, I have an example here of an actual use case where you have your existing web client. It needs to do an IMS transaction on the mainframe. That's where the business value comes from. So you can create, using Akka or using other Java-based tools or any other tools, you can create a web service over your IMS, but you can leverage Akka persistence and Akka clustering to actually control the flows. And Akka persistence and Akka clustering can also give you the ability of event sourcing and replay, which I'll be talking about soon. So this is a high-level view of what that can look like, but when you have messages coming in, you would take your commands and their behavior, and you would create different flows out of them and have them go to your new data stores, your new system of records, and over time, the use of the mainframe where those actual data was residing or where those commands were being executed on slowly go away. You're really, what we're trying to say in the strangler approach is you're just moving away the business flows out of the mainframe. Now, event sourcing. I think this is actually going to be probably the most interesting bit. So this is an integration pattern that you can do on any system, but hold value on the mainframe for other reasons. Because the mainframe contains so many flows, so many data items in such varied ways, you need to create a topology or a system that can handle queries, that can handle creations and updates, and can just have the ability to decompose all of the mainframe operations. This also is important so that by using the reactive concept, you can also reduce MIPS, right? You don't want everything to always constantly go to the mainframe over time. The idea in the strangler approach is also to over time reduce MIPS to reduce the cost on the mainframe. So this is a particular integration pattern that actually is in production, something that I worked on at a previous engagement, where we had a mainframe, and it had SOA-based layer on top. It had TCP. It had all kinds of stuff. So there was an ask. Okay, as we want to move entire business towers out of the mainframe, whether it be your ability to view the profile or update the profile or view a reservation or like the shopping cart functionality that could be embedded in the mainframe, how do you move that out? So if you're trying to do some action, you need to receive that action, and we're calling that like a command actor or an operator actor that receives the command. It knows what to do with that command, and it knows that it needs to talk to some particular actor. There's another actor, which we're going to call a persistence actor, which leverages Akka persistence and journaling concepts to take that command. It knows that that operation is going to cause change in state to various entities, and it makes those changes and also writes to like an event database or to an event log. At the same time, if that command requires change orchestration with a system of record through SOA services, then you just call that particular system of record through SOA-based services or other web services. But the idea is that the persistence actor systems can keep track of all that. And while they're doing all that and creating a separate log of all of these operations, you also send them out to another actor system that we're going to call a hydrator. This guy is making sure that everything that you're doing as you're using the Strangler approach to decouple your mainframe business capabilities is also updating the mainframe. Because if the mainframe is still present within the ecosystem, it still needs to know about all the changes that are happening, because it affects other business functionality, other parts of your company or your enterprise. And that's what that actor system job is, to do a synchronization using any of the previously defined protocols. But yeah, that's pretty much some various integration patterns, some use cases. I think I'm ready for some questions and answers. Did any of these terms sound familiar from those who work a lot on green screens or mainframes? No. I think one comment I do want to make in closing out is that don't shy away from also investigating commercial-based tooling. Commercial-based tooling from IBM or other vendors that expose business capabilities out of the mainframe, they are important. They're important in creating an intermediate state before you can actually fully decouple yourself from the mainframe. My colleague earlier today, Simon Kessler, was giving a presentation on the deconstructing the monolith. From his high-level views, this is just one particular set of patterns that include the Strangler approach, that include other integration flows, that over time you move business value out of your mainframe into other systems.